and the Florida Panhandle had undergone when Hurricane Michael went through. Now, what we'll talk about is quite a few topics here. We're going to try to cover this in about 45 minutes. If you guys have any questions, feel free to reach out. We'll answer them in real time. The first bit is about Hurricane Michael and the damages that were noted after the storm passed, and why strong buildings, or how strong buildings are able to be built when those kind of design events occur. That leads into products that are certified and understanding how wind affects a structure. So we'll talk about how does a building resist wind. And once the hurricane has passed, or let's say even on a normal sunny day, how do we know that the trusses, the load path that we call it, which is basically the ability of the structure to stand up, how do we make sure that that's safe? You know, and how do we inspect it and ensure that our clients are receiving the best opinion that they can with an understanding of the lateral load paths or vertical load paths of the building. And we'll also look at a few case studies and some work that I've done on my own, attic and foundation inspections. We have a few interesting truss inspections that I'm sure anyone that's been in the industry for long enough has already had nightmare stories about. And I also want to touch on the concrete cracking. You know, what is a severe crack versus what is a shrinkage crack? How do we tell the difference? And when we're looking at settlement, you know, one question I frequently get as an engineer is, are these cracks bad? You know, are these cracks settlement? And there's really no way to tell. It's almost like body language. You know, when someone says, well, if they touch their nose and that means they're lying, well, maybe that's true, but you really have to look at all the other parts and pieces of the body, or how they express themselves, to know if that's an issue or not. And the same thing with cement or concrete cracking is, you know, what does it look like when true settlement is occurring versus just something that maybe is minor differential settlement in the course of a building's history. A little bit about me: I've been a general contractor since 2007, an engineer since 2014. I've done quite a few emergency response initiatives in the Florida Keys, as well as working with the Urban Search and Rescue Task Force 1 in Miami-Dade. My goal really is to use the training that I have and the information that I have to help build better buildings, to help rescue folks after a storm if it comes to that, and to help write code, help be a part of the legislative process, so that these buildings, you know, it's with the COVID-19 virus, it is a similar feeling to when a hurricane warning occurs in Florida, meaning that you get this information from the news and you are on your own. You need to get your emergency supplies and you need to stay in your house for a period of time. And what inevitably happens is everyone realizes, wow, the only place I have to go for safe shelter is my home. And, you know, that illegal addition doesn't sound, you know, that sunroom that was built by my cousin doesn't sound so appetizing anymore. That door that we took out or made too large, or that window pane that's really large, suddenly everyone's worried about it. So my goal is to really use this information and help the general public and inspectors understand why this is important. And the reason why this is important, and I'll show a quick video, is because we forget the power of nature. It's very easy for us as humans to ignore or move very quickly into our next topic, and we forget what nature can do. So I'm going to let this play real quick, and you all can see about 1 minute's worth of this hurricane. So this was Typhoon Fani. This was in Indonesia. This was also a record-breaking storm. It was the strongest storm they had ever experienced in that locale in the last decade. And these are 2 or 3 structural failures that occurred in that storm. You watch the roof on this large building. It's a glass roof. The structure completely lifted off. These are children in a school attempting to keep the hurricane door or fire door shut. It's a group of about 10 children. No match to Mother Nature. This one is extremely disturbing because you see the glass pulled from the opening. And so when these things occur, you know, what's essentially occurring is the forces of Mother Nature are pushing themselves against the structure, and the structure is not resisting it. So the structure has a weak point. And it's almost like if you talk about a prison, if any part of the prison is missing, if one bar is missing, if one lock is unlocked, the prison is no longer a prison. So the same thing in a home or home inspection, any part of the chain that's the weak link will eventually or could eventually cause failure. And that's what we're looking for. And we're doing these inspections. You know, I know you guys have a plethora of items that you have to inspect. I only focus on structural. So I give you a lot of respect goes out to the home inspector community for all the things you need to know. But when we look at just structural, it's easy to forget the power of nature. And going back to that Hurricane Michael slide, you know, Hurricane Michael was absolutely devastating for the area because it was the third strongest hurricane on record in terms of pressure. It was the strongest hurricane to ever hit the panhandle of Florida, and it was the strongest hurricane to hit the state of Florida since Hurricane Andrew in '94. So we had extreme design event, which is what the engineers call it. So we've designed these homes. Here comes a design event. It rolls over on between 8 a.m. Wednesday and 8 a.m. Thursday. It rolls over the top of Panama City. This is dawn on Thursday morning, view looking east in Mexico Beach, Florida. So just imagine, you know, on your normal day, your traditional morning, maybe not now, but it formerly used to be, you know, you go down the road, you drive to your favorite coffee place, you drive to your first inspection. Well, imagine you wake up and this is the first thing you see in your hometown. You know, the amount of debris in the streets are eroded, there's rescue workers out. You know, this is not normal living in any sense. And many people have seen this view. This is the view looking east as well that morning. These are probably, in this view alone, I believe we estimated there are over 100 homes that are missing, not destroyed, but missing from the picture. And when this happens, you know, we look at how does wind affect the structure? How does wind work its way around a structure? And how does the structure contribute to it being worse or better? And one of the ways that this occurs is through these eddies or vortices or vortexes, if you want to call them. We call these high suction zones, high suction regions. Essentially what that means is at the areas of corners of buildings, either the roof of the building or the wall corners, what happens is wind has a very difficult time navigating those sharp corners. So as wind attempts to flow around a structure, it's very similar to a really bad day in traffic, except this traffic, instead of following the road or following the rules, it basically says that when the amount of traffic that's trying to get up and over the building reaches a certain point, it has to equal the amount of traffic that's above the building. Meaning that you're trying to fit, you know, 500 cars into a single expressway lane, and you can imagine there's going to be some turbulence there. So in this image, you have a rooftop level, and you can see all of the particulates of the wind as the wind is coming up and over the roof. It's going from the left to the right. It's also causing these small turbulent areas on the solar panels. And what's really happening physically is you're getting this left to right motion from wind, which we call lateral loading. And then you have a vertical motion, which is your suction. And all of that is contributing to either pushing the building or lifting the building. And it may not be the building, but it would be a component. So a truss, a column, an illegal addition, a rooftop solar panel, all of those items can possibly be lifted from the building. And when you look at a high-rise building, it's even worse in that the leeward side of the building experiences a huge negative suction. So in other words, the back of the building will experience, from the bottom to the top, will experience the high degree of suction from wind. And this part is really what can be the most concerning. The front of the building receives positive pressure, meaning it receives water, it can receive some debris. The back of the building receives negative pressure. The negative pressure is for people to grasp, but it can literally pull windows out of the opening. It can pull a door open, it can pull a wall off of the building. And the negative pressure is generally finds its way, or excuse me, it generally will be higher than the positive pressure. So when we look at these buildings, we want to understand how wind travels around them and how wind damages them. So this is, again, a view of Mexico Beach. This is a planned view. In this red square, there are about 32 homes. They are all on slab on grade. They do not have any kind of flood protection. They barely have any hurricane protection. And this is the same view after Hurricane Michael. So Hurricane Michael was able to quite literally displace all of the buildings. Now, this was from flooding and from surging, but there's no way to really tell how much of the building was destroyed before the flood occurred. We do have a few photos from the search and rescue team that was on the at Ground Zero the next day. And one of those is this building. It was built in 1955. And this building has what is notorious in Florida for a weak point, is this gable end. So every time that you see a gable end on the side of a building and you're in a high wind area, and high wind doesn't need to be in Florida. If you're in Colorado, it could be up on the side of a mountain where you have escarpment effects as wind travels up the mountain. Anywhere where wind channeling can happen, in between two other large buildings, you have this gable truss that's on the end, and it's notorious for being a weak point. And why is that? Well, the reason is that the gable truss here tends to want to lay down flat. It doesn't have a lot of resistance behind it. It relies on the plywood and some bracing inside, which may not be nailed well, to stay up. In this case, this is the same building, believe it or not, after Michael. You can't even tell what part of the building was what. But I can tell you that the gable end failed first, the roof lifted, and then the walls were next. So it's a matter of critical importance that we understand how these buildings are constructed and how they're safely designed and how they're safely inspected. And all of those go together. If you look at this building, this is a good example of a building where the wind pressure affected this in such a way that it was able to pull one of the windows from the opening. So if you look, this is 1997. If you want to take a look at this window here on the right, well, sorry, we'll get to that. So this view here is from the front. This area, you see that this entire part of the wall was pulled from the structure to the point that there's actually about a 2 to 4 degree tilt in the structure from vertical. So the structure itself has now undergone severe displacement. And this one is really fascinating because if you look at this window and then you look at the final photo, you really get a sense for that negative pressure, that negative suction we were talking about. So as the hurricane wind blew from the east towards the west, it was able to provide enough suction as the wind wrapped around the building that window opening was literally pulled from the structure. Now, we don't know if it was the window that failed, or maybe it was the wall framing that failed, but one thing is for sure, that the straps and the anchorage that was provided in that house was inadequate to cover the design load that occurred at that time. Now, this building was built in, what did we say, 1997, I think it was. So at that time, the codes were just starting to really recognize the importance and severity of hurricane strapping. It may not have been very experienced, and have quite literally the home is pulled apart at its seams from the wind loading. Now, let me just move this out of the way here. There we go. So the hurricane strapping and load path becomes an important element of any home inspector's analysis. Now, one caveat about hurricane strapping is that you may not be able to see it. So some of these items are not your responsibility because they may not be visible. They may be hidden by decorative structures. They may be inaccessible. But anything that you can see, we really want to make sure that we have a clear understanding of why these straps are so important. And it really breaks down into a load path. So you have up at the top, you have a rafter to the top plate connection that helps provide resistance for the roof to be held down. Then you have sort of a floor-to-floor connection that allows the second floor to stay where it is, and then a sill plate to foundation connection, which allows the rest of the home to anchor to its foundation. A good example of how this fails would be these homes that were built in 2002, again in Mexico Beach, with inadequate strapping, with a high level of lateral loading, with a high level of uplift loading. You end up with very tall, very skinny homes collapsing because of a lateral load. And what that really looks like is if you've got two pieces of wood or two members that are connected, you start to receive this wind uplift, a cyclic loading effect, and the structure starts to shake, the structure starts to move. Hopefully, if the building is built right, this all occurs on a very microscopic level. The structure is moving, you may not even sense it. But if the building is not designed properly or is not able to resist those forces, the building can shake, it can move, it can actually create splits down the fastener. We call that lock shear. So if the fasteners are too close together, or if they're not fastened correctly, or if they're too close to the edge, or they're too large, then you can have a failure. Now, those things occur not necessarily because of an installation defect, but because the wind pressure can be so high, and the installation, sorry, it is an installation defect, but the wind pressure is so high that it literally is able to run up the building, provide a lateral load, as you see here, a vertical load to the soffit as it tries to lift the truss, as well as a vertical load above the truss. So these truss overhangs really have quite a bit of pressure, quite a bit more than what you would think or what you would experience in the rest of the roof. This is a photo I took from the Florida Keys after Hurricane Irma, and I was fascinated, I guess is the right word, because as you see from this photo, all the straps are in place. The straps are there. So if any inspector had visited this job site, he would have given it a clean bill of health, quite possibly, because the straps are there, the nails are in place, they're not, they're not too badly corroded. But in this case, the wind pressure was so high against the overhang that the trusses broke. So it goes back to the analogy of the prison. If one gate is unlocked, the whole thing comes open. So in this case, the building was fine, straps were fine, the main truss was fine, but the overhang was the point of failure. Now this probably would not have been possible to know this would have failed ahead of time unless an engineer had gone in and designed it or had double checked it. So as a home inspector, you may not have seen this, but again, the point would be noticing where are items able to fail and why. My guess on this overhang is this gentleman probably had a large canopy. He probably had some kind of a second floor roofing system, and he just bolted it to the end of his roof truss. And those roof trusses were not prepared to take that additional load, and thus they snapped. When you look at this from an animated level, you also could see what a truss looks like and why at certain areas are under such high stress. So the truss, again, this is on a microscopic level, but it quite literally breathes inside the home. It will vertically displace upwards. It will be held by the hurricane strap. I've got a message here about audio quality. Let me know if you can't hear me, guys. And so those hurricane straps end up resisting the wind uplift and holding that truss down, but it does put a large amount of stress onto the truss. And when this happens, essentially what's occurring is you're having a failure of the main mechanism for the building. So this is sort of a infographic. If you can tell, this is also from the Florida Keys. This is a 2-story building. This is the entranceway to the front door on the 2nd floor. And you notice the walls are displaced outwards. Well, if you were to put that building back together, you would see a truss over the top of the building. You would see 2 walls. And here's what's critical. When those truss straps fail, the walls no longer have the support that they were relying on before the hurricane. And this is why the truss strapping is so critical, because if the truss goes, the walls go, the building goes, everything else goes. So you will find a commonality with many insurance companies are very concerned about how the trusses are attached and how the plywood is attached, because those 2 areas alone can cause a significant amount of damage if fail. And then we have success stories like this. This is a news article printed a week after Hurricane Michael that said every bungalow on this tiny island survived Hurricane Michael, and here's how. And this island was no more than 10 to 20 miles away from the epicenter of where the eye came ashore. So why is this image so much different than the other images that we were looking at. It almost looks like you could move back into this resort right after the hurricane. Nothing seems damaged. The windows are intact. There's some debris on the ground, but for the most part, this island is ready to open and ready to recover. These are other images of similarly built homes, same style. They're called a Deltec home, around their neighbors. Well, this gentleman or woman has no more neighbors because their home survived, their neighbors didn't. Another one here, stick-built home, two stick-built homes across from a Deltec home, completely destroyed, uninhabitable. The Deltec home appears to be completely intact, maybe a few shingle repairs. So how is this possible? You know, many people have seen this image. This is the Miracle House. This is the only house that remained on Mexico Beach after the hurricane passed. And the reason was because it was engineered to 200 miles an hour. The architect and the owner kind of had a competition where they thought it would be, I don't want to say, but they thought it would be, they wanted to make their house stronger. They went well above and beyond the building code, and you see the difference in this house versus his neighbors. So what is the secret? How does this occur? How do we have some buildings that aren't even a building anymore, not even intact, and how do we have some that resist the wind forces? And it really comes down to having a good shape. So these ones have a round shape, which allow hurricane force winds to flow around. We'll talk about building corners in a minute. Building corners can be an area of a weak spot. The building itself is very strong in the way it's set up. It's a circular building held together with radial trusses that meet in the center. So that helps to reinforce the building strength. And then they have tested and certified products. They only use storm tested materials. They only use impact windows. They only use tested strapping. So those Deltec homes, as well as the Miracle home, all utilized a configuration that not only met code, but exceeded code in some places. And the point that I'm trying to make is we can resist the structures, we can resist the load from a hurricane. We can build such that the effects of Mother Nature are mitigated, but it requires knowledge, it requires expertise, and it requires a professional outlook. It requires good home inspectors and good engineers. And then when you talk about products that must be approved for buildings, this is for Florida, but this is very rapidly becoming a nationwide requirement. Florida has a administrative code. This is the administrative code. It basically says that these 8 items must be approved or must be available for approval by the building commission. And they focus on anything that's a building envelope structural frame item. So windows, doors, structural components, anything that would protect you in a hurricane or an earthquake. Those items are what the building commission wants to know have some kind of an approval. And in Florida, we have these 3 areas that we call product certification. We have a Florida product approval, a Miami-Dade notice of acceptance, and then an engineer can provide his own technical report. In the rest of the nation, in Colorado, we have the ICC system. ICC has similar product approval evaluations. And again, they're becoming more and more prevalent around the nation because of fire, seismic, snow, flooding, hurricane. These natural phenomena are not going away anytime soon, so the nation is adjusting. In fact, Congress released about a year ago, I think it was over $1.5 billion to help building departments ramp up their efforts to provide these kind of updates. And these updates are important for home inspectors because it allows you to see what document was used when the product was installed so that you can double check if it was the correct product and how it was installed. FloridaBuilding.org is the Florida system. They have their own database. Miami-Dade.gov has their own database. They have a similar documentation system. And then you have an engineer, such like myself. So I have a hint there. You save my number, 954-947-0880. My website is axiomstructuresfl.com, or send me an email, troy@axiomstructuresfl.com. And an engineer that's licensed in that state, I'm licensed in 4 states currently, can provide a evaluation that would give you the structural integrity information that you need. And then what are we certifying? Well, what we're certifying is the Florida Building Code requires, or any of the codes require, that counteracting structural actions be resisted by structural members. So that means that load paths must be provided. And if that's earthquake or wind, we're really thinking of overturning, sliding, and uplift. and the engineering and the inspections must provide for that. So there's a quick quiz. Which 3 products in this photo require a Florida product approval? You see a lot of items in this warehouse. The 3 that would require an approval just off the top would be a sliding door, a roof panel, and a roll-up shutter. And the reason is because these are building envelope components. They protect the building, and that's where we want to keep make sure that those are properly installed and properly inspected. Now, when we talk about wind pressures, we talked a little bit about wind navigating around corners and high suction regions. You know, these are areas that when you're talking about links in the building envelope, you basically have 4 links. You have wind hitting the roof, which is link number 1. The roof sheathing, the roof fasteners are required to stay in place. Link number 2 is then the trusses. So the trusses need to stay in place and be strapped to the walls. Link number 3 is the walls need to be attached to themselves or to lower floors so that the walls between floors remain. And then the final link is the home itself being anchored to the foundation, putting all of that stress and strain into the earth and grounding the load. When we talk about the wind pressure, we also talk about lateral load path. And lateral load path essentially means a left to right movement or a left to right load. How do we get that through the structure? And these are great images provided by Simpson Strong-Tie, the lateral load from 2 different directions and how that essentially pushes into the building, and then it transmits that load through the trusses. As you can see, anything that's highlighted blue is a truss that has to work together with another adjacent truss to resist those lateral loads. And when we talk about wind speed, higher wind speed is a lot more pressure. So a little bit more wind speed in a different jurisdiction is a lot more pressure. A little bit taller building is a lot more pressure because the wind has to get over the top of the building. And the smaller the area, the higher the pressure. So a smaller window or door, actually a smaller window would have higher pressure requirement than say a door. And the reason is the way that wind averages out over a large area. We also have concerning areas or critical areas, I should say, at the corners of buildings. We call this zone 5. These are usually about 6 to 10 feet in from any prominent corner of a building. You'll notice that those areas require better windows, better doors for wind pressure purposes, or better truss strapping if they're near the edge of the roof. And just the reason, again, is that wind has a hard time navigating around sharp corners. And when that happens, the eddies that are produced can cause a failure in those areas because of the high pressure. Just as a reminder, this is some framing types, wood framing types. We have balloon framing versus platform framing. If you recall, balloon framing is essentially where you're using long studs. You know, they go from the sill all the way up to the top. They have low shrinkage, but they can be a fire risk because of the effect of the fire flue in the chimney, so to speak, in the wall. And then you have platform framing, which is more common for, at least for Florida and for the Southeast, where you're generally providing a platform on each floor. This building is the type that you would most likely see in a hurricane area because of the ease at which you can strap and resist the forces. Now, if you're looking at the trusses and how the joists sit on their members, it's important that we understand that gaps are no good. You know, we don't want to see any gap where these hangers exist because it can rotate that connection. We also want to be careful that the bearing of the joist allows for at least 1.5 inches or roughly the nominal width or the width of the member bearing. So if you look in this image, you can just tell that there's maybe 3/4 of an inch of bearing on this hanger, and that would be a rejection. That would be an unsafe condition because we're not designing for a sunny day. We're not designing for today. We're designing it or inspecting it for a design event, which could be an earthquake where the house is moving side to side, or a hurricane or a high snow event. And we don't really want to rely on something that small. If it were to shift, it may cause a catastrophic collapse. So that would be, you know, something you call out on your inspection report. Incomplete installation of the hangers. If you see that, you know, these hangers have the wrong size attachments, they're missing nails. This one is supposed to have 10 nails, 4 nails are missing in those red arrows. And some things that I've seen on my own that I've been asked to approve. You know, something like this, I say approvable with a question mark, because with engineering calculations, it's possible, you know, it's not a terrible job. Definitely wouldn't be my first pick for how to do this, but as we know in construction, sometimes things happen, and we may need to work with them. So in this case, this may be approvable, but it would certainly require an engineer in the to be called out in the report to come take a look and see if he's willing or can get those calculations to work. And that goes back to the hurricane strapping. You know, we're trying to make sure that the load path is sufficient to resist the storm forces that are approaching. Another pop quiz question. A builder has added an additional load to a wood truss in the form of a water heater. So you get there, you see that the water heater is in the attic, or hanging it from a wood truss. Is that okay? In what circumstances does the International Residential Code allow this? And the answer is going to be C. It's allowed only if that additional load has been verified as acceptable by a certified engineer. So it's not that we can't make it work for you or for your client, but it needs to be reviewed and it needs to be understood in terms of the physics involved. Again, with the joisting and seating, you can see in this photo, this is the same photo with the bad bearing. You can see how the hanger is skewed. So we have a skewed hanger. It's not fully attached properly as well. And what will happen in a design event is those will dislodge, those will come loose. And then a few of typical damages that you might find after a hurricane, or even after a strong storm with a home that's not built properly. You have wind-driven rain getting up under the siding. And when that happens, you start to pull the siding. You can see the effects. It's very deleterious to the structure. The waterproofing system, you know, is not intended to handle punctures or tears, or sometimes it's not intended to handle as much moisture as a hurricane might be able to push up into it. If it's not installed properly, it becomes a very particular nightmare. And siding, roofing, same idea. You know, these things can become displaced and avulsed. And the end zone, we talked a little bit about this zone 5, this effect where on the corners of buildings, you're going to have a pressure multiplier. You would have 3 to 6 feet where the wind speed or the wind pressure is higher, the wind load is higher, and it plays out in real life. When we go and see these after hurricanes, we see areas that are damaged that focus really on the corners and edges of the building. And of course, you have your traditional cracking of beams, you have cracking of drywall at the edges of windows or doors. You know, those are all things that can occur from settlement, can occur from a hurricane load, but it's essentially an issue with the structure that needs to be called out. Now, when we inspect structural damage, one of the critical things that I always teach about, or I always hear questions about, are cracks. You know, when you're looking at cracks, what kind of crack is critical, which kind is not. But basically, you know, vertical cracks, not too big of a deal. Usually it's a drying crack if they're small enough. Horizontal cracks are serious. Those are usually buckling cracks. Those should be addressed immediately. Then you have some stair-step cracks that could or could not be a big issue, and rotational cracks, which are a large issue. So the easiest way to know if a crack is a problem, in my opinion, would be its irregularity is the very first thing. If you see a very irregular crack that's cracking through block, it doesn't follow a necessary pattern, that right away would be a concern to me. And then you start to check these other items. The attic, when you're looking at the attic, you're looking for water staining, wood that's rotting on the underside of the attic. You know, you can use a screwdriver and affect that and check those areas. And you want to inspect, you know, move the insulation, inspect the rafters, check if you can, check the strapping situation. And you may find things that are completely out of the norm, such as this, where you have, you know, trusses on one side, rafters on the other. This is actually, you know, the framer just butted the rafters up to the end of the trusses. And if you're a part of InterNACHI's Facebook group, you'll see more of these. You know, there's millions of homes and billions of homes in America probably, and you will see millions of these damages during your time with InterNACHI and as a home inspector. This is a home that I personally was involved with, and before I knew it, this homeowner or his contractor had completely unwrapped the hurricane strap from the existing truss so that he could use it for his, you know, some other addition. And we said, no, that's not how we're going to do it. He threw in all these crazy parts and pieces, which did not comply. And we had to completely start over because of what they had done. The reason is because truss modifications really can be a concern. You know, the strapping modifications, the truss being cut. You know, we've seen this time and time again where the air conditioning guy gets in the attic and he says, oh, I'm just going to make a little cut. And he basically slices through the entire attic. What's important to remember is, again, as the inspector, if you see this, you might even be able to crawl on these trusses and it doesn't even look like it matters. Maybe it looks like this cut doesn't matter. But you need to refer it to an engineer because it may matter during a design event. You know, we don't know what those members might be required to do when the home is under extreme circumstances, and that's what we want to check. But then when a truss is modified, it can be done, but it needs to be professionally engineered. So this is a good isometric or a rendering of what a professionally engineered vaulted ceiling would look like. You can tell the truss was cut, but you can also tell that substantial structural members were replaced to provide the needed strength back into the system. This was a photo I took February of this year at a home that I was inspecting. I think it was a home inspector actually found this cut truss. You can see this diagonal is missing here. And then he recommended they call an engineer, and then they called me. So I went out there, I looked at this. Of course, this is not code compliant. So what did we do? Well, we develop a drawing. This drawing indicates where the plywood plates need to go at the joints of the truss, and it indicates how to connect those plywood plates. So an engineer can come in, we can essentially reestablish the framing that was missing. We use plywood plates to get the fasteners appropriate, and we made the truss more rigid than it had been before. And this was the repair. Now, if you walk in as a home inspector, you may not know, is this a legitimate repair? Did an engineer provide this? Or is this someone that just took some plywood and nailed it in? So what I always recommend the home inspector or the homeowner to do is, after the engineer does his work and the repair is finished, staple the engineering to the repair. Because if the engineering is present in the attic and stapled there with the proper documentation, then the next home inspector doesn't have to go through this whole system of recommending an engineer. So it's possible that you will see cut trusses that have been properly modified, but it depends on if you have the proper certification to either the engineer's letter to say it's okay, or to call an engineer to have him give you the thumbs up. And the reason, again, is this lateral load path. You know, we want to make sure those trusses can resist not just uplift, which we all know about, but also the lateral movement that is going through the building. Now, the last two items I want to touch on is going to be the shrinkage, severe cracks, and lastly will be settlement. So when we're talking about shrinkage versus severe cracks with concrete, you know, shrinkage cracks, these are common shrinkage cracks. You have some small stair step cracking, you have some corner cracking, maybe a horizontal lintel, a little vertical crack. You know, homes that you may enter might be 50 years old. They're going to crack. They're going to move. They're going to settle. It's part of construction and it's to be expected. However, we need to understand which cracks are normal and which cracks are a concern and which cracks are severe. And how we can sort of tell that, you know, it really depends on how you look at the crack. And again, if you're not an engineer, you need to be able to refer a good engineer to someone if you notice something bad. But here's a good, you know, good methodology for a home inspector. If you're looking at a stair step crack, if the separation along the vertical legs are uniform and there's not a measurable separation along the horizontal legs, so essentially that means that if the vertical leg here, so you can see this is the vertical leg of the crack, it's fairly uniform. You know, it's very small. It's a fairly uniform, it's not irregular. So we probably we would not place this wall moving up and down because it's such a small and non-irregular crack. It's very almost predictable. However, if you look left to right, the horizontal leg, there is a separation, and there's also sort of, there's some chipping, and it's very irregular. So in this case, what we would say is that this crack is consistent with shrinkage because the wall is moving horizontally. It's shearing along the mortar joint. It's not displacing vertically. So if you look at a stair step crack, you want to notice the horizontal and vertical legs and see if you can find a pattern whichever leg, horizontal or vertical, has the most irregularity, has the biggest gap, that may be the crack that will give you the clue whether it's shrinkage or not. And the whatever direction it's parallel to the crack would likely be the direction of the force. So horizontal cracks, probably shrinkage. Vertical cracks may end up being settlement. But if you have a stair step, you really have to look and see how much of these you have and how much of each you have. So let's say you're inspecting a 1-year-old house, you've got a slab on grade, you notice that there are hairline cracks in the concrete floor, but there's no vertical displacement, meaning nothing has moved down or up. You see the cracks, but it is mostly flush. What does this indicate? Well, typically, it's a 1-year-old house. It would be unlikely that it would have long-term settlement at this point, and you have no vertical displacement. So in this case, it could be normal plastic shrinkage. A famous quote in construction is, if it doesn't crack, it ain't concrete. So concrete cracks, it's what it does. And by understanding that, we know, well, maybe these cracks aren't a concern because this is normal plastic shrinkage. There's no vertical displacement. However, if you're able to put your hand in the crack, or if you're able to put a baby through the crack, then you know that you've got an issue. You know that you have what we would call a severe crack. So what I kind of say is anything that's 1/8 of an inch, anything exceeding 1/8 of an inch, I would call it severe cracking, or would need to be looked at. Some people use a penny, or they'll use a quarter. If you can get a penny or a quarter inside the crack, you probably want to call an engineer, because you were not sure what exactly could be the cause of that. Now, if you've got hairline cracking, what you want to look for is correlation. So if you see some hairline cracking on the outside of the structure, go ahead and take a look inside and see if the drywall is cracking too. Because if you've got that correlation, now you know that it's probably not shrinkage. It's probably a severe crack, because now you've got the wall is moving enough to displace the finish on the inside. And that's the picture you see on the top left is the drywall on the inside of an inspection, where the top right is the outside. So you can see that on the outside, there's these irregular cracking, very small, but very irregular. It looks like it's been repaired. Coming on the inside, the drywall is cracking. I would call that a severe crack, because you've got correlation in the structure.
Hey, Troy.
Yes.
We have a question about cracks that's related to what you're talking about. John asks, what about a vertical crack, and it's small, goes from floor to ceiling, and you can see light through it?
Not good. Not good at all. I don't have the picture up here, but I actually have one with one of the InterNACHI inspectors, Dennis Bonner. It was a crack that was repaired. He asked the homeowner, may I pull the sealant out? I think it's important. The homeowner said, sure. He pulled the sealant out, and sure enough, he could see light from the other side. Huh. So if you can see light through it, I would call that severe. And again, you may get lucky. The engineer might come out there and then he says, oh, it's just some concrete voids, or it's just this or that. But generally, if I'm called out for something where you can see light through, it's usually going to be something that's not intended at all.
Cool.
Sound good?
Yeah, thanks.
Okay. And then this was a good example of how it almost went wrong. So I was called, a home inspector said that he noticed, you can just barely see it in this photo, there's a horizontal crack running along this corner here. And where the wire meets the ground, or starts to head towards the ground, I was able to put my finger underneath the foundation. I was able to get my hand under the foundation. And this is what concerned the home inspector. So the home inspector, rings the alarm, says an engineer needs to come look at it. The homeowner hires me to come out there. And these homeowners were so excited to buy this home. It was their first home. I mean, I really emotionally was attached to them, and I wanted it to work for them too. And I almost said it would be okay. But I started looking, and I said, well, the foundation, you can get your finger under it. That's not good. There's a little crack here. That's not good. But maybe just maybe with some small repairs, it's no big deal, and it hasn't gotten as bad. But would you mind if I just went inside and took a look? And they said, sure, no problem. And I went inside, and I went into this bedroom, and then I said, would you mind if I just pulled this carpet up? And they said, no problem. And sure enough, when I pulled the carpet up, there was a textbook 45-degree crack right on that corner that had already occurred. And when you see this, the foundation has already failed. You know, you've already lost your structure in a sense. It's got to be repaired. And that was a fail. So that was, you know, they need to use a retrofit for pin piles, which I'll cover at the very end of this, on how to fix that. Real quick, minimum allowed slope of graded soil next to a building. Great, got to be greater than 6 inches over 10 feet. So essentially you need, if you're in a building like this, you want to see in the course of a 10-foot span on the outside of the building from the wall outwards, you want to be able to see a 6-inch drop, you know, and you don't really see that here either. So new buildings, you want to see enough drainage away from the building so that this issue doesn't happen. And when it doesn't happen, this is what it's going to look like. So this is the retrofit of a residence. This residence was had settled. This was back in the 90s, and they did a repair. So how this happened is they have 2 additions on the home, front and the back. And they have these odd-looking steel members on the outside of the wall. And when we start looking at them, we start realizing that, you know, wait a minute. There's, first of all, there's an illegal addition here that was not on the appraiser's sketch, right where these metal components are. So we start wondering what's going on. Then when you look at the front door, you start seeing there's a substantial crack in the column, a substantial stair-step crack in one of the room connections. This is the measurement of that column crack. I mean, you really can see there's a lot of movement. You know, concrete does not bend like this unless it's under a lot of force. So something's happening with this building. And then back to that correlation. You know, how do you know a crack is important? Well, if I'm on the outside and this is where the crack, you know, you can barely even see it in this photo, and you look outside, it's barely a hairline crack, maybe a bit more, a 64th of an inch or something. But when you go on the inside, look at this. The drywall had cracked up to maybe 3/8 of an inch. Okay, so on the outside, you see a small crack. On the inside, you see a substantial crack. That would be severe because of the correlation, because you're seeing that the building's not only moving, but it's pulling the finishes along with it. And what does it look like in the rest of the building when you have a severe settlement issue? It looks like this. You have cracks that are extending up the walls, through the beams, up the ceiling, through the next bedroom, through the next ceiling, through the corners of the ceiling, through the next ceiling. And basically you have a map that looks like this. So you can see that the entire left side of the house is settling. And those are cracks that those are severe settlement cracks. Those are obvious. Those are much easier to tell. And that would warrant an investigation. Now, what we noticed on this job when we were called out to visit it, this was this year, was that there was some old documentation in the city that basically had an old engineering firm. They had come out there in 2006. They were notified about the same cracks. So these have not been repaired in 14 years. And those engineers basically said, well, we observed step cracks, which are still there. We observed a horizontal crack, which is still there. And we observed additional cracking along the outside of the residence. So what they said is this is settling and we need to do something about it. And what they recommended was either helical piers or push piers. And these helical piers are essentially provided where they're driven, they're rotated into the ground, and they're able to provide substantial support for the foundation. They're driven into bedrock or some kind of better strata, if you will, whatever is in the site. You may have to go down many, many feet for that to be possible. So I'll just show as a quick animation of what the helical pile looks like when it's installed. I don't think we have sound. Okay, so you have a Caterpillar comes in. They're able to place the helical pile shaft. They drill that down into solid strata to whatever the engineer specifies. You can tell here they probably went maybe 20, 15 feet. Then they're able to put this anchor plate on, this L angle, large bolts. They apply pneumatic pressure. They lift the home back to its original where it was before it settled. They pull the pneumatic equipment away, and then they bolt everything in place. They cover it all up, and now you've got a reinforced home structure. So that was Ramjack. Ramjack is a foundation company that provided that video. And the alternative to helical piles would be pin piles. Very similar. The only difference is these are more or less pushed into the ground instead of rotated. You're able to open up the soil, apply the pneumatic pressure to lift the home, underpin everything, completely support it, fill it back in, and you're all finished. So what that looked like for this project was you would get a push pier plan. So you have an engineer, you know, the home inspector would come, call out settlement as a possible issue. The engineer would come, confirm it. A geotechnical engineer would then take tests of the site, create this map, figure out where those reinforcements need to go. And this was the original residence. This was the map that those engineers had for this project. And I just thought it was fascinating, this area that had all those push piers that we saw in the grass, those metal components. Those number 1 and number 3 had to go 24 feet down before it finally reached anything worth putting the home on. So, you know, some of these homes that you will inspect have pockets where they're literally built on peat or dirt, moss and organic material. And you won't know it. You know, you can see that the other ones only had to go 4 to 6 feet and they were fine. So why did number 1 and number 3 need to go that far? It could be anything, but the point is that we don't know until we investigate. So, you know, dealing with hurricanes, dealing with load path, dealing with concrete settlement and cracking, you know, these are all parts of the home inspector's toolbox that hopefully you all are continuing to sharpen. And it only increases every year. The codes get more complex. There's more and more requirements from the municipalities about how they want their safe structures to be built and inspected. And there's more and more people that rely on certified inspectors like yourselves to make sure that the right people are getting eyes on these, that engineers are called when necessary, and that overall we provide a safe structure and a safe place, a safe shelter for the residents that are going to be inhabiting that area. So I thank you guys for listening. If you have any more questions, I'll happy to take them. There's my email if you want to send anything privately. And you know, I appreciate you all having me on.
It was really great presentation, Troy. I really appreciate it. We do have a question from YouTube Live. Corey asks, what about separation vertical gaps between brick veneer walls and the door framing? It's a hard question without seeing.
So you're saying there's a gap between the brick and the door framing?
Yeah, and the brick veneer wall. So it's maybe not a load.
Yeah, one of the important areas, and I may have a quick a diagram for this. One of the items that comes up frequently when this occurs, especially with openings, doors, windows, things like that, is shimming. So if you're able to tell, or you can notice if the finish is removed or whatever, what have you, if you're able to tell that shimming has taken place in that structure, if there's any kind of gap that allows movement of those anchors, in a storm, you're going to see, you're going to have a problem. And I'll show you this animation real quick. Let me see if I can unlock it. Hang on one second. We're going to go hide. I'm going to share the screen again, Ben. Can you see it or no?
Yep, give it a go.
Let's go. Can you see that?
Let's see, it didn't pop up for me.
I'm going to share one more time.
Okay.
Okay, see that?
I see you're starting to share your screen. There you go. Yep, see it.
Okay, so in this case, if you want to imagine that door jamb, and you're looking down on the door jamb,
yep, and
the brick or the host structure is up at the top there. If there's a gap, what happens is this: you end up with this rotational effect where the fastener is moved, the primary seals are broken, and the fastener is distorted. So you want to limit that as much as possible. Generally in Florida, we limit that to 1/4 inch.
That's awesome. Where do you get these good videos? I wish I had them.
A lot of time.
Did you say, are you correct that the strength of a negative pressure around a building during a windstorm can be stronger than the positive pressure?
It can be, yes, especially on those corners that we talked about. So on the outside or the corners of the building, you have a higher negative requirement than you would have on the on other areas of the building.
Yeah. So when we're training home inspectors, where do you look for defects? It could be those, what did you call them? Zone 5s, the end zone 5s.
Right.
Because there's a lot more pressure going on. Negative.
Right, exactly.
They're pushing in and out. And if you're thinking about moisture,
right.
Well, moisture can go in any direction in one of those areas.
That's true. That's true. And the wind can come from any direction. You know, there's a misconception that, you know, there's prevailing winds in a hurricane. That's really not true. They can come from any direction. So if you're, you know, if I'm inspecting, and I can access the corner areas, then I will try to get there, especially for the roof strapping. Because if the corner areas are secure, then you know the rest of the house has got a good shot at surviving. Yeah.
And also, I really like the joist bearing and seating on a joist hanger, closing the gap. And you mentioned 1/8 of an inch is your tolerance, and that's pretty tight.
Yeah.
You know, if I go back in my memory, you know, it's very rare that I see absolute close contact between the joist end and where that joist hanger is attached. There's always some kind of issue that it was too tight, and when you slide the joist down, it's kind of like in there and not. Yep. But your tolerance is really like
Simpson,
1/8 of an inch.
Well, it's not my tolerance. I mean, I agree. 1/8 of an inch is pretty extreme in my opinion. Now, that doesn't necessarily mean that you can't have a gap larger than that. It just means that the certification needs to be there. So Simpson allows larger gaps, but I think they put a line where it's supposed to be measured from. So then the overall gap is a little more, or they say add more nails for it. But it's just something to look out for. You know, I think a big part of being a good home inspector, or being any inspector, is knowing your resources, you know, and being able to read the signs. You know, maybe that modification of the truss isn't so bad. You saw the one that I approved that I did. It doesn't look that great. So, but it matches the calculations. So you have to use all of your judgment, all of this training, you know, so that you can understand, well, okay, maybe it doesn't meet the technical part of the code, but the manufacturer might have provided additional testing, or there might be additional supporting documentation that we don't have yet.
Yep. I actually had a real estate agent say to me that what you just mentioned in your presentation is just a little cut. It's just a little cut. Oh, what's wrong with that? But I always wondered why don't engineers just you know, heat stamp or ink stamp their modifications, so that, like you said, that the next home inspector comes in, we know it's been modified in approved, engineered way.
Yeah. I think that's where the industry is going. I think that construction is one of the last industries to be affected by the digital age. We're very, you know, paper and pencil controlled in construction. But you are starting to see things like QR codes that link to, you know, a website that tells you what was certified, or, you know, those homeowners that staple the engineering to the truss. It's very archaic, but it works. So I think that those are going to become a lot more prevalent. Especially for home inspectors, where you'll be able to scan something and see the history of that product.
Well, Mr. Bishop, thank you very much for your time teaching us a little bit more so that we can be better inspectors, and for being available for